Hello everyone, I'm Sandeep. Here in this YouTube playlist, we are going to discuss about the Verilog implementation of SHA512 algorithm. Well, SHA512 algorithm is an cryptographic algorithm which generates the hash function. Well, it is mostly used for password protection applications. And then let me tell you one basic application of SHA512 which will give you an idea about what SHA512 algorithm is. In many systems, passwords are not stored directly because the password what we set won't be able to appear for the provider also. So, in such cases, passwords stored as hash values to enhance the security. SHA-512 algorithm is such a cryptographic algorithm which generates the hash function. Well, for different for different passwords there will be in different hash functions, so there won't be a same hash function for different passwords. Here I am just selecting the FPGA board. Maybe in future I will implement this entire Verilog code in the FPGA board. I have the available FPGA board of RTX 7 family. So I am selecting that corresponding FPGA which I have in my lab. Now I am giving the module name as SHA512, which is the top block of our entire Verilog code. In from this block we will call different modules by using the module instantiation. Now in the SHA512 algorithm, the message and the message is the input and the hash function is the output. Okay, the message can be of any size, but here instead of doing these padding and all unnecessary stuff, we are simply assuming that the message input size is 1024 bits. Okay, and the hash function size is 512 bits, that is a standard one. Whatever maybe the message size, say from 0 to infinity, the hash function size is 512 bits only. Here I am typing 1024 bits, later I will change to the 512 bits. Okay, uh, please understand that whatever may be the input size, the generated hash function is 512 bits only in the crypto hash 51 SHA-512 cryptographic algorithm. Here in the screen you can see that mi is the message bit that I want to encrypt, and w0 to w71 are the words that need to be generated in the process of generating the hash function. Here in this video we can discuss about The Verilog hardware implementation of the generating block, which is used in the 51 SHA512 encryption algorithm. Okay. Now in the on the screen you can see that the message bit is divided into 16 words, each consists of 64 bits. From those 16 words, we need to generate another 64 words, which finally total of 80 words. That is used in the further implementation of the SHA algorithm. So in this video, we will focus on about how these 80 individual words are generated. Now we need the 80 words which is of 64 bits each. Okay, for first few words, like from 0 to 15 words, we will generate directly from the message function itself. In the diagram which is showing on the screen, you can see that from w of 0 is generated from the MSB 64 bits of the message function. Similarly, W1 is generated from the last but one MSB 64 bits from the message function. Like that, from the message function, from the message which is of 1024 bits, you can generate 16 words from the message. Okay, and remaining 64 words we have to generate from the previously generated 16 words. Okay. Now I am writing the word generating block in a separate module, which will be called from this main module by module instantiation process. In this word generating block, we have four inputs. From the from the generation diagram, you can see that there are four inputs to the word generating block and one output coming from the word generating block. The word generating block involves the modulo addition and sigma functions which were applied on the two two of the four inputs. Okay. Now let's get into the word generating block. Here on the screen you can see that in the word generating block there are four inputs named as in1, in2, in3, in4, and the output named as out. Each of the ports have 64-bit in length. From the diagram you can see that only the inputs in2 and in3, which were in the diagram as w1 and w1 and w14, in2 and in4, okay, were went through these sigma blocks. Remaining two inputs in1 and in3 directly applied to the modulo addition. Now we will declare the outputs of in2 and in4 as the sigma 0 and sigma 1. Okay, now let's get into what these sigma 0 and sigma 1 blocks will do. Here on the screen you can see that there are only two functions, rotate right, shift right. Okay, so sigma 0 and sigma 1 blocks involve only rotate right and shift right. Rotate right here means circular shifting. Shift right shr means not a circular shift, only linear shifting. That means we have to add zeros for the remaining locations. Okay, now let's write the Verilog line for this block. Here for shifting we are using, instead of the shifting operator, we are using the hardwired connections. Like for example, if I want to shift here one bit, so what I am doing is, instead of shifting the operator, after the shifting, what the output will look like depending upon the input. So here I was hardwired that input, so the output is like a shifted version of the input. Now we are declaring the intermediate output because we need to perform modulo addition, not a normal addition. So to perform, why do we need to perform modulo addition means, for example, here we are adding the 4 bits, like 4 different inputs. Like if at all in any case, if the output is more than the 64 bits, we need we need to fit that output into the 64 bits only. Okay, so for that purpose we need to perform modulo addition. Here modulo addition will perform, here we will perform modulo addition by doing AND operation with the all with the maximum 64-bit number. Here maximum 64-bit number is all ones in the 64-bit field. Now our word generating block is ready. We need to instantiate this word generating block in our main SHA512 top level block. Now based on the block diagram, here the 4 inputs are W0, W1, W2, W14. Okay, kindly note this, that W0, W1, W9, W14, these 4 words are directly generated from the message itself. Now we need to generate remaining 64 words. To generate remaining 64 words, we need to use these already generated 16 words. Okay, so you can see on the screen that the words that I used are W0, W1, W9, W14, which were already generated. Okay, by using these words, now I am generating my first word, which is W16 from the word generating block. Similarly, like this, we need to instantiate another 63 different word generating blocks whose inputs are from the previously generated blocks. So for up to 16 blocks, we have the inputs from the previously generated. Up to 4 blocks, we have the inputs from the previously generated blocks. Okay, from the fifth WGB5 block onwards, we need to use these W16, W17, these words are Now what I am doing is I am merging or concatenating all these 80 individual words into a single large word, so that I can use this thing in the future implementation of the SHA512 algorithm. Now at this point we are successfully generated the all 80 words. Okay, now we will see the output of all these 80 words by writing a test bench program. As here the message input what I'm giving is 1024 bit, so I'm declaring that message as register, because in the test bench the inputs are declared will be declared as registers and the outputs will be declared as wires. Okay, here the since the message input is 1024 bit, so I'm declaring it as 1023 down to 0, and since the output hash function is 512 bit, so I am declaring it as 511 down to 0. Here you can see I am giving the test bench signals. Okay, I have the few different cases which were the names, so that actually most of the people will store the password, will kept the password in terms of names only. Okay, so I am giving the different test signals. If you can see the, for example, take the name rslab at the rate hash. For this name it will hardly store rclab at the rate hash 7. So 7 into 2 14, 14 into 8, 14 into 8 bits means 4 8 32 3. mm, Hardly it will take double one 2 bits only, but I need to require 1024 bits in length, so I am padding extra 968 bits. Okay, so that I can give the message input as 1024 bits. So here only I am padding the bits. If you want to pad, you can write the separate Verilog code for padding also. Now let me execute the program. Okay, you have to click run simulation, as you all of know. Now mm, See, this is the output. Here in the hash function, we are getting all z z z z z z. At present, we don't need the hash function. We will generate this hash function after generating all the blocks. At present, in this video, what we are focusing on, the word generating block only. So let me open the word generating block outputs. Here you can see the word generating block outputs. 511 down to 0, 5111 down to 0, and then each individual words also here it is appearing. As you can see in my previous explanation, I concatenated all the generated 80 words into a large word so that I can use that large concatenated word in the future blocks of SHA512 algorithm. So as of now, this is the word generated block output for my different test cases. If you like the content, like, share and subscribe the channel. If you have any doubts, comment down below. I will try to answer the doubts. Let's wait for a few more days for the upcoming videos in this playlist. Next, in the next video, we will going to discuss about the round block. Similar to word generating block, there is a round block section also, which is a part of the SHA512 algorithm, which will be our next video.